Okay, so thank you for continuing on with the linear structures webinar series. So this one will go through setting up a torsion and bending test of a chassis. So this is a follow-on from yesterday. So if you weren't here yesterday, feel free to watch the recordings that are all uploaded. So with this one, this is a basic setup of correctly setting up a torsion and bending test for a chassis vehicle, for the chassis of a vehicle, and this is how it's done by a top level European sports car manufacturer. So the way I'm going to set it up is how they set up their models and analyze them as well. So hopefully you'll be able to take this and put this into your models for when you start doing the chassis analysis. So what I have here is just a generic model of a FSA car chassis that was kindly donated by Canterbury University. So they've actually given one of their older models for me to be able to demonstrate here. So what's already set up is we'll just quickly go through it. So remembering from yesterday, panning around, control, left click, and we'll zoom in on it. So as you can see here, where the axles would be, or where the car is joined, where the wheel is joined to the car, we're using RBE3s, not RBE2s, because we've got to transfer the load. So if you remember from yesterday, the RBE3 transfers load and RBE2 transfers stiffness. So that's already set up there as if we're going to mimic that on the ends of each of these rigids, we would have wheels. And you'll also notice in the center of the car there, we've got another RBE3. So that there is to transfer the bending force through the chassis. So for the setup of this, it's quite important that you get your constraints right. So what I'm going to do is I'm actually going to go through the constraints of this. Okay, so for the torsion test, and also you'll notice that I've already got my load collectors set up and split out, as well as my load steps. Not to worry about the components, as this was a carbon fiber chassis which I transferred to a simple aluminium metallic chassis. So in the load collectors, what we're going to do is we're going to set up our torsion constraints first. So we're going to make that one current. Now with the constraints on an RBE3, you can't directly put a constraint onto an RBE3. So what we have to do is create a bush in between, and we can create that rigid. So we can make a rigid bush which has extremely high stiffness. So it is basically like we have the constraint on the RBE3, but to the program we technically don't. So what we do for that is I'll create a component for this. Create component bush. Make sure that's correct. And we're going to put this on the rear of the car for the moment. So what we need to do as well is we need to create some nodes and translate them out. Now this can be done simultaneously with both sides, so it's always handy to do that, because with the bending we are going to have constraints also on the front of the car. So what we'll do is go to geometry, create nodes on geometry. Create geometry, create nodes. Sorry guys, I just lost my train of thought. Sorry, go to mesh, create 1D elements, springs. And now, so what we've got to do is we've got to duplicate and translate a load, but this is how we this is where we would create our bush. But first we're going to translate the node from here outwards. So geometry translate. Sorry, that was what I was meaning to do before. Now, what we need to do as well is we're going to duplicate the nodes. So we need to select the nodes that we want first. So I'm selecting all to one side. Just put that away. Then you click on the nodes box and you can hit duplicate. Now for this, we're just going to translate the nodes out, say by 10 units. And we're going to put that on the y-axis and we're going to translate that negative. And we can see that's just slowly moved out from the axle. So if we zoom in there, we now have a gap. We should have a gap there. And what we're going to do now is we're going to clear those. So by pushing this arrow, we've now cleared those nodes and we're going to do the same on the other side. Select both the nodes, but this time it'll be a positive translation and they've moved out too. So then we return out of there. Oh, sorry. Just have to do that again. Translate. Just make sure they've moved. Sorry, that's why I didn't duplicate. So duplicate, always remember, it's very easy to mess on up. Then translate, now return, and now we've got our nodes there. Perfect. Okay, so we're going to create our C bush or our bush. So we go now to mesh and we create 1D elements. And this is going to be a spring. So we click on the springs. And first things first is change the element type to a C bush. Okay, and now you select the two nodes that we want. So we're going to go around and go node, node, and now we can see that it's green. And then we go down here and we do them all. So all the nodes that we've just created, we're going to create a bush, C bush element between the two. Okay, so now once that's created, we jump. So we do need a property for this, but we'll create the property now. So create property, and we'll just call this the bush. Okay, so for this, we need to change the card image from P shell to a P bush. Yes. And then select the K line, and then you just select K1 rigid, all these. So this makes it a rigid bush now. So this gives you a rigid connection onto your RBE3 element. So now we then assign the property to the component, and that's done. So now what we can do is we'll apply our constraints. So we'll do our torsional constraints first. So for the rear, we're going to make sure that's highlighted. We're going to go boundary conditions, create constraints. We're going to select our node. We're going to zoom in. So just select one at a time. Now for one side of the rear, just making sure I've got, yep. One side of the rear, you're going to constrain it in the 1, 2, and 3 degrees of freedom. So it means it's not going to translate neither X, Y, or Z, but all rotations are open. So we create that. And now we go to the other side, select that node, and then we only constrain this in the 1 and 3 degrees of freedom. Create. Okay, so while we're still creating our constraints, so we're going to then make our bending constraints current. And for the bending, all you want to do is have it constrained in a degree of freedom number 3 on both sides. So we select our node, just degree of freedom 3, create. Then the other node, create. Okay, so the reason why we only constrain this in the degree of freedom 3 is because that is the translation in the z-axis, and with bending, that's the only movement we're going to have, or with that load applied. But you still want to allow all rotations. And so now our constraints are done. We'll jump out of that, and now what we can do is we can retranslate these nodes back to the axle. So what you can do is go back to geometry, translate nodes, and now we can click on the nodes we want to translate, and now we just do the reverse. So where we did a negative translation, we'll do we'll do a positive translation for those two. Now we've put them right onto the axle, and then clear those, and then we select the other two sides and do a negative translation return. Now you can, if you want, clear these nodes, where if you want to, you can go geometry, delete, then nodes, and you can just select your nodes if you want. For this, we'll just leave them on there, but you're more than welcome to do that as well. Okay, so, oh, hang on. Sorry guys. Yeah. Okay, so just to make sure the audio was okay, we just had a quick pause. So, what we're going to do now is we're going to apply our loads. So we're going to make sure that our torsional loads now is we're going to apply this first, is make current. So with this, when we do the torsion and bending test, all we're going to use is 1 Newton of force. Why that's really good is because this is a linear analysis, you're then able to scale up the displacements found. Yeah, sorry. So what I've actually then forgot to do as well, sorry guys, is you've got to set a system for the bush. So we're going to go into tools and analysis systems, and then we want to select our nodes or assign set to nodes.
Hey guys, sorry, I'm just gonna take over for this for a quick second because I've only just showed Joel how to do this, so I'll show you guys as well. So because the C bushes are 0 length now, they don't have an axial direction defined, which would usually be the one axis. So we need to define a coordinate system for them to use. So what we do is we go to card edit, this little icon here. We choose elements, and we choose the config type to be a spring, and the type is a C-bush. So it's a C-bush, and then we click edit. Oh, sorry, we need to select them by config as well. So we go spring and C-bush, and then they select all of the C-bush elements. So you can see down here it says 4 elements added. Then we can click edit. And you can see some of them, the entities that are different between them. So this is the element IDs are all different. GA and GB are the 2 nodes that are connecting up, so they're all different, but the property is the same for all of them. And we can set CID. So this is the coordinate system ID. Now, if we have a coordinate system for the model, if for instance we were using C bushes to model bolts, we could have a different stiffness in the axial to share directions. And then we'd use a coordinate system to define that orientation. For this instance, we've got it all set to rigid, so it doesn't matter. So in CID, if we set 0, then that just tells it that we're using the global coordinate system. So we can just return out of there, and that assigns it. So you can basically see the global coordinate system here in the model. So if everything's aligned to that, you can use the global coordinate system. But otherwise, you can define your own if you want to. Okay, I'll pass it back to Joel for the rest of the demo.
Thanks, Alex. Yeah, sorry about that, guys. Sorry. So that is something that I'm actually just learning now. So as you can see, even myself still learning with it all. But yeah, so hopefully that was clarified. So when we translated it back, so it's got a 0 displacement, you do need to set up the coordinate system with it. So that's what Alex was going over there, just to help me out. So we'll go back to setting the load. So as I was saying, with it, we only use 1 Newton loads because it's very easy to then, in a linear analysis, you can scale it up, and then the scale can then be times by the amount of that. So if you use 1 load and you do a scale factor of 10, the displacement then you scale by 10, and that's what you should be able to roughly see with a 10 Newton force. So with this, that only works with a linear analysis. So if you're doing non-linear, you can't just scale in that way, to make that very clear. So you need to be very careful with that. So we'll return out of there, and we're going to go and create boundary conditions, create forces. So all we're going to do is create an up and down 1 Newton force on either side of the front end. So what we're going to do is change to the z-axis, so the magnitude, or from the vector to the z-axis. Select one side, 1 Newton, create, then select the other side, give it -1 and create, then we return out of there. And now what we're going to do is we're going to assign the bending force. So we make the bending force current, and we're only going to apply 1 Newton in here. But to make sure you actually get the right node, what we can do as well is hide components. So we're going to hide all the elements just to make sure that we select the correct node here. So now we've only got our RB3 showing in the middle. It's boundary conditions, create force on the node. So now we've definitely got that one, and that's going to be a -1 Newton force downward on the z-axis. So then we create that, return. Okay, so we've got all our loads and constraints created. Now, what we need to do in the load collectors. So for the torsion, it's very straightforward. All we need to do is create a simple load step, call it torsion, and add in a lineostatic analysis type. Your SPC will just be your torsional constraints, and your load will be your torsion loads. However, in the bending test, because now we want to keep the torsion constraints, but we also want to add in the bending constraints. What we do is we create a load collector called SPC add. So when you do that, you create the collector, and then you change the card image to SPC add. Now this is how you can add constraints together. So if you have 5 constraints that you want to run with the same load, then what you do is you create an SPC add card, type in the number of constraints. So for ours, we're only adding 2, type in 2, hit the data set, and this is where you choose which one. So I've only opted for 2, and I've added in the torsion load collector. You select that, then you go torsional constraints, and that's it. So now what we've done is we've added the 2 sets of constraints, and this will then now be able to go to the bending in the load step. And instead of adding bending constraint or torsional constraint for the SPC, we add in the SPC add load collector. And then for the load, we just have the single load, the bending force. Does this make sense to everyone? So this can also be done with forces as well. So you can have, so it is worthwhile when you're creating these load collectors is just have a look through some of the card images, and then in the help sections, have a look through what you can create. So you can create different load cards, and this will be very different for running non-linear analysis as well through OptiStruct. So you will be using a lot of these through them. You can do motion. So it is, and this is where you find your EIGRL cards as well from yesterday. So we've created those. We've applied them onto the model. And now what I'm going to quickly show, what I didn't get quite to go through yesterday was the control cards. So as you can see up here, we've got cards, got a few there already, but the main one I want to go through is the global output requests. So to find this is we go to analysis on the radio button, click control cards. So none of them here are green, which means I haven't selected any of these. So when we go next, we'll find that global output request is already green. So that means I've already selected some. So I'm going to open that up. I'm going to show you what I have selected for this. So we've opted for displacement because that's a pretty big thing for this. We want to know how far this displaces from the force applied. You can go down and you can choose energy, element forces, fluxes. You can really choose a lot out of these. So this is where you probably spend most of your time when setting up your cards. You've got pressures. You're going to go SPCF. So this is for your SPC forces, your strains, and your stresses. So that's what we're using at the moment. So they're the output requests that we've asked OptiStruct to give us when we run the analysis. So then, like yesterday, return out of there, and that will then automatically come up there. You can also go to output, which is further along. And in your output, you can select how you want it. So I've just asked it as a H3D. I don't want that many outputs, so you can change that to just one output, number of outputs, then change the keyword again to H3D. So that's your standard output file for the Hyperview. We want all frequencies, so everything. You can return out of that. Now you're ready to run it. So we click on OptiStruct, save your .fem file into the location you want. If you can, put in your line and proc 4, so number of processes 4. You don't have to do that though. So then you would hit OptiStruct and you would run the analysis. So once, and this is another thing I was hoping to show yesterday, but I ran out of time. Once the analysis is completed, you can open up the .out file. So this will become as a .out file, which you can open up just in any text editor. And this is also a look at what is also running. So you'll get a screen that'll be running down as it's performing the analysis. And this is where in the optimization runs as well, you can actually go and have a look at the .out file and see how your objective has changed. So this is where you can view the mass changes. But for this one, we're not running an optimization, so we're going to be having a look at a few different things. So it tells you number of elements, number of rigid elements, constraints, degrees of freedom. So this gives you an idea as well how long this can take to run, like how many equations you're going to be having. Because remember, every degree of freedom is going to have an equation. You've got your 4 sets, types of elements in there as well. So that's very handy to know what kind of analysis you're running. If you've got this set up as a full model and you don't want any shell elements, you can come in here and you can see you've got shell elements. So then you're able to know, well, hang on, what's going to be given to me may not be correct. So then you can stop it before waiting the hour for your run to finish. You can stop it, get everything set, and then go again. Sets up all your parameters. So you guys, when you run your analysis, I recommend definitely going through these and understanding what's coming out, just so you have an idea. And then it's got analysis results, and that'll show that. So then we open up our H3D file, and then from this, what we can do now is, this is where the outputs come in with the result type. Click down, and now you can see we've got our SPCF, forces, moments, elements, strains, and it will tell you the 2D and 3D, stresses 2D and 3D, but also our element strains and stresses in our 1D elements, which is our rigids. So that also outputs for them. So make sure that you do know which elements you're looking for. So if I'm looking for stresses in the 1D, I've got to make sure I select this one, not the 2D and 3D ones. But for the start, we're just going to have a look at the displacement of the torsion. So we're going to apply that. Now we can see how far this is moving. So should be able to set the animation. And just having a quick look here. So we'll keep it at linear, but one way to do this, so because this is linear, it's not moving, but what we do is, this is where we up the scale. So by clicking the little bending, I don't know how to explain it, it's a little bar with a red arrow going down. We can change the scale to say 100. As you can see, it still hasn't changed a whole lot, but we did see it slightly move. So we're going to make it 1,000. Now we can start to see only very slightly. So this would be now 1,000 newtons applied in this way. So let's put it up to 10,000. And now we can see the displacement and what's actually happening within the chassis and the warpage. So we can see large displacements here and some really big warpage and shape change happening within this area. So this will give you an idea as well of where you need to be applying stiffeners, where the stiffness is lowest in your chassis. So where you can increase this, because, and we can see here, if you can tell where my cursor is, where we've got the up force, we had it on the other side, in that little corner on the join bit is where we're seeing a huge amount through this area here. So, and it's also same, a lot of change within that thinner area. So we know that we may need to increase the stiffness there, but that's also at 10,000 newtons up and 10,000 newtons down. So Whether the chassis will ever see that much force is also a different thing, but that comes down to your engineering judgment and also some of the constraints that the FSAE will put on for their testing as well. So if the FSAE has their own test that they expect you guys to run, set the model up how they've told you to do it as well. But if they don't, if they've only told you just the force to use, then it's good practice to set it up like how I've shown, but use the force that they've told. So making sure when you do this, you are conforming to either how they lay it out, or if not, always go with a 1 Newton load, because it's very easy to scale up or down should you wish. Okay, so that's our torsion. Now what we're going to do is we're going to change the subcase to subcase 2, which will be bending, and we're going to apply that. So as we don't see as much shape change here, but what we will do is we can then increase this from 10,000, let's put it up to 100,000 newtons. There we go. Okay, so where's my mouse? There it is. Now we can see some serious change. So as we can see here, as that 100,000 newtons is pushing down, our constraints are holding, and we can see a huge amount of warpage within the side wall here. And there will be a lot of stress in there as well, so we can always change that. Go back to contours, and you can always change that to stresses. But this is the displacement, so this is at a scale factor, remember, and that's what we're seeing there. So again, with the bending, if they tell you to use 100 newtons downwards, do your analysis with 100 newtons downwards. Or if they tell you to do it with 1,000 newtons, use 1,000 newtons. But again, if that's not laid out, it's always handy to start with a 1 Newton base load. It's just like when you first run a CFD analysis, always run a flat plate compared to starting to run your wing. So you've got base results to compare to. So it is very much like that. But again, if they're telling you to set your model up one way, set it how it conforms to the rules laid out by the FSAE for the competition. So yeah, sorry about taking up the time today, but this is what I was hoping to get through a bit more yesterday, but we were running out of time. So is there any questions with this? And sort of what's actually happened here and why you would do this? Does anyone have any questions with that? Feel free to speak up, because I mean, look, I'm more than happy to stay around for another 20 minutes if you do have questions, so it could be a good opportunity to. Hopefully by now, sort of at the end of the third session, guys, if you are new to CAE, you're starting to see a real good benefit as to how you can implement it into the designs, and how you can start to use this within analysis as well. Or also if you have been using CAE for a number of years, hopefully I've been able to show you a different way of looking at things, and you're starting to think about more advanced techniques such as proper mesh correlation, and you've been able to go through some of the tutorials online, and you're starting to get a little bit of a handle, hopefully, on the programs. But yeah, look, if there's no questions there, I will leave it there. So this is just a good generic way of setting out your chassis torsion and bending test. A bit about control cards, so you can start to pull out the desired outputs, not just defaults. And hopefully this is starting to help give you a bit of an idea about how to do some post-processing as well. So definitely have a play around with all the different things, like your ISO plots, different contours, what you can view, different types of analyses, and just seeing how you go there. So always check out the tutorials in Altair University, because there is a heap there. Oh, okay. Perfect. Yeah, that's a good question, Ben. So this process of actually doing it won't change between composites and metallics, but more the actual setup of the material and the property will be very different. But the actual running of the bending and torsion test will still be the same. So in a later date, I'll be going through how to set up a composite model, and going through the layers and the plies. So in terms of running the actual analysis, it's the same, but the actual material and the properties created for your analysis will be very different. Does that answer the question? No worries. So yeah, no, that's a very good question, because so sometimes things with composites will differ dramatically between metallics. But in this case, it won't. It's just going to be the actual setup of your model, not so much the setup of your loads and load steps. So what I'll do is I'll stop the recording now. But look, if you have any more questions, please feel free to ask, because I can easily leave the meeting open for a little bit longer if you'd like to sort of have a bit more of a chat about some stuff. So I'll stop the recording